Mr. Odell here. We're going to talk about d orbitals today whenever we're talking about electron configurations. So let's jump into it. First off, we're talking about the idea of a d orbital. Sorry about the bad handwriting. So we know that d orbital has a d orbital shell. Let's see. Sorry, I haven't used the software before. There's my erase button. So we know that our d orbital shell follows the same trend as our other orbital shells. So my s shell, we know, has one orbital. My p shell has 3 orbitals, which means my d shell, assuming it follows the same trend, is going to have 5 orbitals. This is equating to the s shell holds 2 electrons, p shell holds 6 electrons, and my d shell holds 10 electrons. So, that being said, we now have this idea of how many electrons our d shell can hold. So we still follow the same trends where we singly fill and then we doubly fill that we talked about in a previous lesson. So looking at our energy ladder that we talked about previously, if I can draw a straight line. So we have our energy going up. So our first energy level, our lowest energy level, is going to be my 1s shell. Our second lowest is going to be my 2s shell. We know that the second energy level also has a p shell. So then we're going to have a p shell. So from there, we're going to move up to our 3s. And then we're going to have our 3p. So once we hit our fourth energy level, we see something kind of weird happen. And I'm going to try to just make sure that draw this away from the other ones. So I'm going to have my 4s, which would follow our pattern. But what's going to happen is we're also going to see our first d orbital shell. So the issue being this 4s and this 3d orbital shell are both really, really close in energy. My 3d has a slightly higher energy than my 4s, but they're close enough that electrons can sometimes move between them. So we know electrons can sometimes move between them. Now, this only occurs whenever we're talking about the fact that it would make it more energetically favorable to make our electron config more energetically favorable. So I'm going to leave this up here. We can continue this energy ladder if we want. So I want to walk through, just add a couple more layers. So we're going to have our 4p, we're going to have our 5s, and our 5s and our 4d are going to do the same thing. And this would keep going. So there's our 4s, here's our 5s, or sorry, 4d, there's our 5s. So let's look at an example. So this first one is just going to work exactly like the electron configurations that we've already done. So we're going to look at the example of, let's go with cobalt, which just confirming real quick, I think cobalt is element number 26. Could be wrong on that one though. It might be 27. Yeah, it is element number 27. So what this tells me is cobalt has 27 electrons. So first looking at our orbital notation, so our ON, we're still going to follow that same pattern as normal. So I have 1s. We know our s orbital can hold 2, so 2. 2s, 2. 2p6, because we know that's the next up energy level. So just going to count for my electrons real quick. So we're down to 17 electrons. Next we have our 3s, 2, and 3p6. That accounts for 8. Puts us down to 9 electrons. So we have our 4s next, because it's slightly lower than my 3d. That is going to hold 2 electrons, which puts us down to 7. And then we're going to have our 3d, which puts us at can hold 7, because we know our d shell can hold 10. So with that being said, let's also look at our line diagram. So our LD. So first we're going to have our 1s, which is going to have 1 up arrow, 1 down arrow. Next we're going to have our 2s shell. So still up arrow, down arrow. Next we're going to have our p shell, which has 3 orbitals. 2, 3. This is not 3p, this is 2p. So we're going to singly fill all the same orbital spin, and then we're going to doubly fill. We can shorthand this because we know it's a full shell if we really wanted to. So next we're going to move to our 3s, which is 1 orbital. Same deal. We're going to have our 3p next, which is once again 3 orbitals. We know it's a full shell, so I'm just going to shorthand fill. Okay. From there, we move to our 4s, which is a full s orbital. So, and last but not least, we're going to have our 3d. I'm going to draw this one down below. So we're going to have 5 orbitals in my 3d shell. So first electron goes there. We're going to singly fill each one with electrons, all the same spin as my first one. So let's go ahead and do that. So we accounted for 5 of our 7 electrons in our 3D shell, which means I'm going to have to doubly fill 2 of these electrons with downspin, since we did upspin first. So there is our electron configuration, both in orbital notation and in line diagram notation for our cobalt. So stop the video. Finish writing that down. I'm going to go ahead and erase this. So I'll give you a second to copy it. And I am erasing starting now. Real quick, I'm going to redraw my energy level diagram. So we have 1s, 2s, 2p, 3s, 3p. We're going to jump up above here. We have our 4s. And we're going to have our 3d. And these two, remember, are interchangeable. So whenever we're talking about d orbitals, because these two energy levels are so close, there are 2 weird exceptions. So there are 2 exceptions to the normal filling pattern. So our first exception is going to be if I have 4 electrons in my D shell. My second one is going to be if I have 9 electrons in my D shell. So we're going to walk through an example for both. Real quickly, we're gonna erase this. That way we have a little bit more room to walk through our two exceptions. So our first exception is going to be our 4-electron exception. So we're going to look at chromium, which is Cr, and it should be element number 24, which means I have 24 electrons. So real quick, I'm going to walk through my orbital notation. We have 1s2, 2s2, 2p6, 3s2, 3p8. We're going to count our electrons real quick. So we've used 18, leaving me 6. Next, we're going to fill 2 in our 4s shell. We're going to fill 4 in our 3d shell. So because we know that this should be 3p6, because we know that this is always going to be the same, so my 1s through my 3p6, we're going to ignore this for now. So what we're going to do is we're going to look at our line diagram notation, our line diagrams for our 4s2 and our 3d4. So our line diagram for 4s, we know an s is only 1 electron. It is doubly filled. So we're assuming everything prior to 4s is all completely filled. Next, we're going to have our 3d shell, which can be 5 orbitals, once again, because d shells have 5 orbitals. This is going to be 3d. And we have 4 electrons. They're all going to get singly filled. So talking about this from an energetic standpoint, we know in the chemistry community that there are 2 really, really stable forms of electron configurations. So our most stable electron configuration forms. So the first one, the most stable, is a full shell. So if I had an entirely full 3D shell, 3D shell where I had 10 electrons. So my second most stable is having a half full shell. So what I can do, right now we have a full 4s shell and we have a 3D shell with 4 electrons. In this particular instance, what I'm going to do is we're going to move this electron right here over into our 3D shell. And what this does, if we redraw this, so we have our 4s with 1 electron, and then we have our 5 d orbitals for our 3D shell. So we have electron, 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 and then our 5th electron. So what this does is this gives me 2 half-full shells. So in this case, my 2 half-full shells are going to be more energetically stable than my full 4s shell and my 3D shell with 4 electrons. So anything in the same group on the periodic table as chromium is going to exhibit this exception. So if you go down the row from chromium, or down the group from chromium, you will see the same pattern over and over. So real quick, we're going to look at one more. So I'm going to try to keep a good bit of this here. So we're going to, because all this electron configuration up to our 4s and our 3D is going to be the same. So just trying to make this go a little bit quicker for video's sake. Okay, so we're going to re-add our line again. Okay, and we're going to look at copper, which is Cu, and we know this is element number 29. Wait, let me think about that. So that's 18, puts me at 11, 2, 9. Yep, okay. So it's element number 29. So with that being said, normally we would fill 2 electrons in my 4 shell, which puts me down to 9. And then I have 9 electrons, so we'd singly fill first 5 times. And then I'm going to doubly fill with the opposite spin 4 times. So once again, following these energetics rules, where my most stable is going to be a full half shell, and my least stable, or sorry, my second most stable is going to be a half full shell. What we can do is we can take one of these electrons from my 4s, and we're going to move this over to here, inserting it in my 3D. So redrawing that real quick, I have a half full 4s shell, and then I'm going to have a full D shell. So the reason this one is more energetically favorable is because our 3D shell is technically slightly higher energy. So having that in a more stable form than because what we're doing is we're trading a full 4s shell for a full 3D shell. But notice my 3D shell is going from 9 electrons to 10, so it's going from 9 to a full shell, whereas my 4s shell is going from a full shell to a half full shell. So from an energetic standpoint, the bottom one is going to be more energetically stable. So this one's going to be more energetically stable. So that being said, pretty much everything outside of these 2 groups, so the group with copper in it and the group with chromium in it, are going to follow the traditional, we're going to fill 4s first, and then we're going to fill 3D. So coming back here, we know copper is going to be 4s1, 3d10 because of that. So if you guys have any questions, shoot me a message on Schoolg. There is practice problems. Hunter pointed out to me yesterday that 2 of them would take F orbitals. So for Wolfram, so you're going to skip Wolfram, and you're going to skip Mercury, so Hg. So you're going to skip both of these 2 problems on the practice set. All right, guys. So that's going to be it for the video.